So yeah, our next speaker is Tianmin Shu. Tianmin, can you try sharing your screen?
Yes. All right, can you see the slide?
Beautiful. All right.
Great.
The
All right,
stage is yours.
yeah, so thanks so much for having me here. So I'm going to talk a little bit about how we can develop benchmarks for evaluating human-level machine social intelligence for AI models, and especially how social cognition study can help us to achieve that. All right, so as the ground vision for AI, in the future, we will have to, or we will want to have AI systems that can live with people and help people in the real world. And in order to develop such AI system, they must also have human level machine social intelligence so that they can understand people and interact with people in the same way that human can understand and interact with each other. So, but unfortunately, we currently do not have many benchmarks for evaluating human level machine social intelligence for AI models. Now, to fill this gap, in recent years, my colleagues and I have developed multiple benchmarks for machine social intelligence to evaluate different aspects of social intelligence. And in each of these cases, we took inspiration from classic studies for human social cognition and followed their kind of experimental design to create trials for evaluating whether AI models also understand these different aspects of social intelligence. So in this talk, I will only focus on the most fundamental aspect of social intelligence, which is intuitive psychology. So what is intuitive psychology? Well, it is intuitive psychology is the ability to reason about hidden mental variables such as the goals and the beliefs of agents by watching their actions. And this comes very naturally to people. It's part of our common sense, and it actually develops very early on since infancy. So for example, if I show this animation and watching this animation once, you can immediately recognize the goal of this agent. You can also understand that in order to reach its goal, the agent needs to take the most efficient action, maximizing the reward, minimize the cost, subject to physical constraints. Now, the problem is how we can evaluate intuitive psychology in machines. Well, to answer that, we can take intuition from developmental psychology, where researchers have designed many experiments to evaluate what kinds of basic concepts in intuitive psychology that babies can understand. So inspired by these studies, we create a benchmark called Agent, where we create trials, thousands of trials that can be organized into 4 scenarios, probing different concepts in intuitive psychology, including goal promises, action efficiency, unobserved constraints, and cost-reward trade-offs. And all of these trials followed the same paradigm, the violation or expectation paradigm. So I will use scenario 1 as example to show you how this paradigm works for evaluating these different concepts in intuitive psychology. And specifically, this scenario is inspired by Woodward 1998 studies. Okay, so here's an example trial for scenario 1. There are 2 phases. In the familiarization phase, you'll see 1 or more reference videos of agent's typical behavior in the environment. So for example, in this video, you should be able to see the agent will look around first and then decide to pursue the balloon cylinder on the right-hand side. This establishes this agent's preferences of this balloon cylinder over the other objects. Now in the test video, you'll see, in the test phase, you'll see a video of the same agent, but now in a different environment. So notice that the position of these 2 objects are now swapped. And the behavior of this agent in the test video could be either expected or surprising. So for example, you expect the agent to pursue its favorite object, the balloon cylinder, but you were surprised if the agent suddenly decides to pursue a different object. So now, the original study showed that baby can understand this. They will watch the surprising condition longer than the expected condition, showing their understanding about goal premises. All right, so for all these different scenarios, they follow the same formalization and test structure, but they probe different concepts. Now, how we can evaluate models in these trials? So for a trial, we'll ask the model to give us a surprise rating for a test video condition on the corresponding reference videos. So this will be a surprise rating for the expected test video, as well as the surprise rating for the surprising test video. And the model's judgment is correct if and only if the surprise rating for the surprising test video is higher than the surprise rating for the expected test video. All right, so more than that, for each scenarios, we also have multiple types of trials. And these different types of trials within the same scenario, probably the same concept, but they are visually and structurally different. So for instance, in scenario 1, we may have several subtypes like this. And in these different types, we have different numbers of barriers between the agent and objects. So this crucially allows us to evaluate the generalization capacity for an AI model, just like what Tao mentioned in his talk. So for example, in this case, we can evaluate a model in this leave one type of condition where we'll test the model on this scene type. All right, so now how we can build a model that can understand this basic concept in the intuitive psychology. So in our work, we developed this method called BiPAC, which combines Bayesian inverse planning with core knowledge, specifically the kind of core knowledge that's advocated by Liz Belkin in her earlier work. So given the videos, the BiPAC model will first detect objects and agents from these videos, and then we can recreate a similar environment, approximate physical environments in a fixed engine by proposing a set of physical variables describing the physical properties of the entities here, such as the mass and the friction environments. And then for agent, we also have a set of agent variables. In this case, it would include agent's reward and cost. So condition on these two sets of variables, we can then sample trajectories that will maximize the reward and minimize cost for the agent. Compare that sample trajectory with the observation in the video, we can estimate how likely you will actually observe this trajectory from the video, condition on the hypothesis about these two sets of variables. Then we can conduct Bayesian inference based on the prior and the likelihoods to interpret the behavior of these agents in the video. So now how we can actually get the surprise rating in this case. So first we can infer the latent variables from the formation videos. This will give us a sense about the agent's reward and cost. And then we can predict agent's expected behavior in this new test video, condition on both the inferred variables and the initial state of test video. And then we can compare that with the observation and define the surprise rating as the differences between the prediction and the observation. Now, this is our method, but there has also been an alternative way, a more precisely end-to-end way to build a model that can try to understand intuitive psychology. So specifically, there's this theory of mind neural network developed by researchers at DeepMind that could also be applied to this benchmark. So TomNet will first encode all these reference videos into latent variables, which hopefully will tell you something about this agent's typical behavior. And then condition on the latent variable as well as the initial state of the test video, TomNet will then go ahead to predict the trajectories of these agents in these new test environments. And then similarly, we can define the surprise rating as the distance between the prediction and the observation. All right, so now how these two types of model works. So first in our benchmark, we have a human baseline. So here the solid line shows the mean and the shady area shows the standard deviation. So you can see human perform generally pretty well in this benchmark. On the other hand, when we test TomNet in this leave one type of out scenario condition, TomNet cannot really generalize well to this unseen type. In contrast, our BiPAC model, which crucially includes core knowledge about the physical world and how agent plan, do generalize well even in this unseen scenario. So this shows that in order to really understand this basic concept in intuitive psychology, a model needs to acquire knowledge about the physical world and also understand how agents can plan under various physical constraints. I also want to shout out another kind of complementary benchmark called BIP, developed by Moria Dillon and the Branton Lake's team at NYU. So similarly, they also follow violation of expectation paradigm to evaluate intuitive psychology AI models. But they generate similar in agree words, and they focus on different kinds of scenarios. But in the end, if you really want to evaluate an AI model for intuitive psychology, you should evaluate that model on both benchmarks. And for both benchmarks, the data set in these benchmarks has also been used recently to study human social cognition, and specifically because the data sets are so much larger than the previously hand-designed traditional kind of stimuli in your previous empirical studies, and also the stimuli can be easily controlled by procedurally by a program to procedurally generate richer kind of patterns. It's a lot easier for us to test different kind of hypotheses that cannot be easily tested using the traditional kind of stimuli. All right, so just a brief summary about what can we learn from this one example. So we can learn that AI can benefit from social cognition. Specifically in terms of benchmarking, we can first know what kind of basic concepts that we have to evaluate for AI models and how we can evaluate them, and how those different concepts in social cognition, social intelligence can be related to other aspects of intelligence, for example, in intuitive physics. But we also can learn that cognition can actually benefit from AI. So we can have larger scale kind of empirical studies, but also we can try to build a new type of computational models for human social cognitions. And all of this present great opportunity for interdisciplinary collaboration. And I think this is this seminar, this workshop more broadly is a great opportunity for us to try to establish such collaboration. With that, I want to thank you again, and I'm happy to answer any questions.